Physical Science. This is Mr. B, and today we are starting Chapter 13, and the title of this chapter is Forces in Fluids. So we just got introduced to forces last chapter, and any push or pull on an object, and we have discussed fluids before. Again, general term, just a gas or a liquid. So we're going to look at how those two things can be related, how pushes and pull on objects can relate to interactions with fluids, which again are gases and liquids, or just a general term for fluids. So we're just going to jump right into it with our first section, and the title of this section is Fluid Pressure. So we've talked about pressure also within this year sometime, but we'll get a little bit of review about what that is. So to start, they give a real, I think it's a really effective real-life example of pressure. It's comparing two types of seats. It says because the theater seat exerts a supporting force over a larger area, it is more comfortable than the bicycle seat. So I think if we all had the choice to watch a movie to sit in either in a theater seat or a bicycle seat, we would all choose the theater seat, and it has solely to do with pressure. The theater seat is larger, so that means it's a bigger area, so that means that the pressure is kind of more spread out, or the force is more spread out rather than just being concentrated into that one area, so that's going to result in less pressure. And so to figure out actually how pressure is calculated, we are going to divide the force by the area over which the force acts. So I will give an example, or here's our little calculation right here. So pressure, I would definitely write this down, is the result of a force distributed over an area, and we can calculate it out pretty easily. So pressure equals force over area. So what this equation means is the larger our force is, the larger our pressure is going to be. The smaller our area is means the larger our pressure is going to be. So if we have a large force but it's distributed out over a large area as well, then our pressure is not going to be as great. Again, the theater seat versus the bicycle seat. So just for some calculation purposes, the unit of force is the Newton, so we all know that. And area is the meter squared. That should be squared. It shouldn't just be meter to the meter squared. And so now our new SI unit, which you would probably definitely need to write down for pressure, is the Pascal. And a Pascal is just 1 Newton per square meter. So a Newton over meter square. That's, again, just what we would expect when we calculate out a problem anyway. So we call this unit, though, of pressure the Pascal, and we're going to figure out why here in our subsequent sections, because there was a scientist by the last name of Pascal who did a lot of work with pressure. And so we have a little sample problem here. Again, it's just simple. If the area of a box touching the ground is 1.5 square meters and its weight is 2,700 newtons, what pressure does the box exert on the ground? So it's just plugging in our known variables. Our force, 2,700 over our area, 1.5. We divide that out, and it's 1,800 newtons per meter squared. So you can see right here we have newtons on top, meters squared on bottom, so our unit is newtons per meter squared, and that translates into a Pascal. And then if you notice, we talked about all of our prefixes early on in the year. I know that's been a long time, but a kilopascal, so we moved it to the thousand, so move it over 3 spots, and so we have pascals. And to make it a little more I don't know, numbers a little bit more manageable to work with, we can change it to 1.8 kilopascals, and that's still the SI unit. We're just adding one of our little prefixes in front of it to make the numbers a little bit more manageable. So that's pretty simple pressure problems. Yes, force over an area. And if we made this area smaller, so if our area, let's say, was only 1 meter squared, then our pressure was going to go up. But if we made our area, let's say, 3.5 meters squared, then that's definitely going to make our pressure go down. So the larger area we distribute the force over, that's going to lower the pressure. Again, I just think that bicycle example is a really good example. And so that's how we calculate out pressure just in general. And so now we're going to take a look at how water pressure can change with depth, and then how pressure can be distributed at a given level in a fluid. So now we're going to relate not pressure to maybe so much as a box touching the ground, but to what our fluids are. And we'll just go ahead and we'll jump right in with what a fluid actually is first. So a fluid is a substance that assumes the shape of its container. That's our definition of a fluid. Again, we've talked about that when we talked about fluid friction, but a good general definition for a fluid is a substance that assumes the shape of its container and our general examples are both liquids and gases can be classified as a fluid, and so they just list here below water, oil, gasoline, air, helium. Again, any other gas or liquid you can think of could be classified as a fluid. Our next part, just a little bit review from the particles, and we talked about this in our states of matter way back at the beginning of the year, but particles in a liquid are more tightly packed together, but they're able to slide past one another, to whereas our particles in a gas are going to be more far apart, and they're going to travel in straight lines until they collide with one another, with another particle or an object. Remember, we said pressure inside of a closed container is actually because the collisions of the particles with the wall. So, quick review, particles in a liquid, they are tightly packed, but they can slide past one another. Gas, they're more spread out, and they just kind of bounce around until they collide with one another. And so because of this, water in a glass is in contact with the walls and the bottom of the glass, and it exerts a pressure on these surfaces. So for a fluid that is not moving, depth and the type of fluid are the two factors that determine the pressure the fluid exerts. So the deeper you are down, the greater pressure you're going to exert. Again, I think that kind of makes sense. If you're at the bottom of the ocean, you have a lot more pressure exerting downward on you than if you're at the top part of the ocean. So depth, that's just how deep the fluid actually is. That will help determine what the pressure is. And I think I might have actually skipped a slide, so hold on, let me go back here. Oh yeah, so we have water pressure increase. I knew there I was skipping something. So water pressure increases as depth increases, which is what I just said. And the pressure in a fluid at any given depth is constant and is exerted equally in all directions. So if I'm at 500 feet below the surface, the pressure is going to be equal all around me at that certain depth. If I go up to 400 feet, then the pressure is going to be different than 500, but at 400 it's all going to be equal as well. So sorry, skip that slide there. And then for this one, it says each vase holds a different amount of liquid, and the liquid levels are the same because pressure depends on depth, not on the amount. So all of these are exerting the same pressure on one another, and you can see they're all kind of in the same row here. So all have equal pressures across the board because they're all at the same depth. They're all, if randomly one of these arms extended below sea level, maybe then we might have a little bit different pressure in this vase, but that's not really a logical situation. So even though they have a different amount of fluid in each one of these arms, they're all at the same pressure. And so that is pressure kind of dealing with the water. So now we're going to do with our other main fluid, air, and air pressure is going to decrease as the altitude increases. And you probably know this because if you go up into the mountains, the oxygen gets a little thinner, it gets a little bit harder to breathe, and that's because there's generally less air there, so there's less air pressure. And kind of a little question they're going to ask us here to deal with Earth's atmosphere. Again, atmosphere is made up of gas, so it's exerting a constant pressure of about 101 kilopascals at sea level. So why doesn't that air pressure crush us? And that is, hopefully we might have a little simple answer, that because the pressure inside our body is going to balance the air pressure outside, and then the balance forces cancel, resulting in a net force of 0, which is kind of what we've been talking about with kind of Newton's with the equal and opposite reactions and everything like that. So Earth's atmosphere is constantly exerting a pressure onto us because it has that fluid pressure, but we are constantly exerting it right back at the same balanced force. And so our last couple slides here is just an example of kind of how we can change the air pressure and we can actually cause it to crush something. So if we have a can containing a small amount of water and we can heat it up until the water boils, then we can cap the can so we can close it off, and as the can will cool off, the pressure inside the can becomes less than the pressure outside the can, because as it cools off, the particles are not going to collide as much, so therefore they're not exerting as great of a pressure, and then the difference in the pressure will actually crush the can. So this step 1 here, you can see this can is on a hot plate, so then they cap it, and then you can almost see kind of almost right away as it's starting to cool off too, that the pressure is going to start get to it. Pressure gets to it even more, pressure gets to it even more, and the can is finally crushed. So I know that's our first section. Going to kind of cram it into one here, but that's it for all of section 1. So make sure you let me know if you have any questions.